All right, folks, moving right along to Newton's second law. This is hopefully going to be one of the shortest videos because this law is an equation. So let's get to it. Newton's second law is definitely the most important of Newton's three laws. It's also the idea and equation you will use the most all year. So Newton's second law is referred to sometimes as the law of acceleration. And it says that a system's acceleration is directly proportional to the net force on the system and inversely proportional to the mass of the system. So, said another way, a system's acceleration depends on the net force. Now, there's a symbol that we use when we talk about proportions or proportionalities, and it's the Greek letter alpha. So this set of symbols means acceleration is proportional to net force. What that means, and what you've seen in your lab by now, is that if you graph acceleration versus net force, you would get a straight line that passed through the origin. And so what a proportionality means is if two things are proportional, then if one of them increases, the other increases. If one of them decreases, the other decreases. Any change in one is mirrored by the same change. So if the net force goes up, then the acceleration goes up. But it gets way more specific than that. If you take the net force and you multiply it by 7, then the acceleration is also multiplied by 7. This multiplied by 7 is referred to as the factor. Multiplied by a factor of 7, things that are proportional will change in the same way. So that goes for increases and decreases. It does not apply in this way. If the net force has 40 newtons added to it, then the acceleration will have 40 meters per second squared added to it. That is not how that goes. So when we talk about things that are proportional, we really just talk about like multiplying them and dividing them by the same factor. That's how proportional things change together. Right. Inversely proportional to the mass of a system, we can write a different way. We can say A is proportional to m to the negative 1 power, or A is proportional to 1 over m. And so what that would look like, and what you saw in your lab, is if we were to graph acceleration versus mass, we would get this curve, where if the mass is very low for a net force, the acceleration is very high, and if the mass is very large, the acceleration is very low. But proportionalities, we can write them in the way that they're written. So if we do something kind of crazy, if we graph acceleration, I say crazy, I mean crazy in terms of like physics. If we graph acceleration versus mass to the negative first power. So if we take our data and we take all the masses and we take the inverse of all the masses, we will then get another straight line that passes through the origin. So A is proportional to m over 1. And so we'll work with this sort of thing throughout the year. And it means weird things like if m to the negative first goes up, then acceleration also goes up. Now, we tend to not think about things in this way. We tend to think about the actual variables. So another way to say the same thing is to say if the mass goes up, then acceleration will go down. If things are inversely proportional, then those variables will change in exactly the opposite way. So the things that we end up saying would be like if the mass is multiplied by 4, then the inverse happens to acceleration. Then the acceleration is multiplied by 1/4. If you have 4 times the mass, then you get 1/4 the acceleration. And so that's what an inverse proportionality looks like. That is not the equation that is Newton's second law. The equation that is Newton's second law, and kind of the reason you're here, is an object's acceleration is equal to the net force on the system divided by the mass. Or, as you will almost always write it, net force equals mass times acceleration. And so that is like so important. It is worth putting it in a box. This equation is the essential equation of this whole course, since this is a course on mechanics. And so we will use this all the time. And so this is an equation that has two vectors in it, net force and acceleration, and they're the only vectors, and they appear on opposite sides of the equation. And when that happens, you can usually say that these two vectors have the same direction. In other words, an object will accelerate in the direction of the net force. Now, that doesn't mean it will move in that direction. We will break that rule repeatedly, but it will always accelerate in the same direction as the net force. So the velocity will change in the direction of the net force. We will work with Newton's second law a lot in 2 dimensions. And just as a little connection, if A equals 0, then net force equals 0. And we just talked about that. That's Newton's first law. So Newton's first law is baked into Newton's second law. But Newton's second law is something that we can take a lot further than Newton's first law to understand a lot of things and why they work.